So just as we had before, uh, now we have another example of a linear transformation, and I want to see the interplay between the nullity of t and the rank of t. Um, let's look at this one. Certainly it's linear, that's an easy check, but let's calculate the dimension of the null space and the dimension of the range of this one. Um, so how can we proceed? Well, this transformation that we have here is given by a matrix. Which matrix? So T may be summarized in the following way. It's x1, x2, described as 1, 1 times x1, x2. So, well, we have the following identification. To work with the null space, we introduce as an augmented matrix. But well, this is already in row reduced echelon form, and reading off, we get that a vector x1, x2 belongs to the null space of T if and only if x1 plus x2 is equal to 0. Well, that's not a surprise, right? It's from this one. So we have that x1 is equal to negative x2, and x2 is whatever it wants. Thus, I have this x1, x2 is equal to negative x2, x2, which is equal to x2 times negative 1, 1. So, the set containing the vector negative 1, 1 is a basis for the null space of T. Thus, the nullity of T is equal to 1. Now, what about the rank of T? To calculate the rank, well, just as we had before, remember, we introduced a very similar matrix. But now, with this extra condition, with this extra element, I'm sorry. And, well, we perform reduction, but it's already reduced. So there's nothing to be done, which means that we can simply say that the rank of T is 1. And now we have nullity to be 1, rank to be 1. And as I said before, we're looking for some sort of compensation. So this says, well, if I add the nullity and I add the rank, I get the dimension of the domain. So that's a conjecture. We need to prove it. I think it's true. So here's the following claim. Let T be a linear transformation from Rn into Rm. Then the nullity of T plus the rank of T is equal to the dimension of the domain. Well, let's prove that.